I am B. Janardhan Reddy. In this video, I am going to tell you about the electronic configurations of the first 20 elements in the periodic table. First, I will show you the first 20 elements in the periodic table with their symbols and samples. See here. The first element in the periodic table is hydrogen. Its symbol is H. Next, helium He, lithium Li, beryllium Be, boron B, carbon C, nitrogen N, oxygen O, fluorine F, neon Ne, sodium Na. The Latin name of sodium is natrium. So, the symbol of sodium was derived from its Latin name natrium. So, it is Na. Next, magnesium Mg, aluminium Al, silicon Si, phosphorus P, sulfur S, chlorine Cl, argon Ar, potassium K. Its Latin name is Kalium. So the symbol was derived from its Latin name Kalium. So the potassium symbol is K, and calcium Ca. So these are the first 20 elements in the periodic table. For them, I am going to show you how to write the electronic configurations. Okay. So electronic configurations. Actually, what is electronic configuration? How the orbitals are filled by the electrons. What are the rules that must be followed while writing the electronic configurations of the elements? All those things we are going to learn in this video. Okay. So what is electronic configuration? Here is the definition of electronic configuration. The distribution of electrons into the orbitals of an atom is called as the electronic configuration. Isn't it? So the distribution of electrons into the orbitals of an atom is called as the electronic configuration. Every neutral atom consists of a fixed number of electrons which is equal to the number of protons and is called the atomic number. So while writing the electronic configurations, first we know what is atomic number. The atomic number is nothing but the number of protons present in the nucleus of an atom, or the number of electrons revolve around the nucleus in case of neutral atom is called as the atomic number. See here. Now let me tell you what is atomic number. The number of protons in the nucleus or the number of electrons revolve around the nucleus in a neutral atom is called the atomic number. Isn't it? See here. This is a nucleus, contains 6 protons, and neutrons also lie in the nucleus, but here I am not showing the number of neutrons present in the nucleus. Protons and neutrons of an atom lie in the nucleus, isn't it? And electrons revolve around the nucleus. So the nucleus of this atom has 6 protons and 6 electrons revolve around the nucleus in different orbits. See here. In the first orbit, 2 electrons are revolving, and in the second orbit 4 electrons are revolving. So the number of protons is equal to the number of electrons revolving around the nucleus in case of a neutral atom. So the atomic number of this atom is 6. It is nothing but carbon. Carbon, its nucleus has 6 protons and 6 electrons revolve around the nucleus, and number of protons in the nucleus is 6 and the number of electrons revolving around the nucleus is also 6 and atomic number is 6. Okay, so the atomic number is nothing but the number of protons present in the nucleus or the number of electrons revolve around the nucleus in a neutral atom is called the atomic number, isn't it? While writing the electronic configuration of an atom, we use a standardized notation or method called as Nlx method. So in this Nlx method, what N represents, what L represents, and what X represents. See here. So in Nlx method, N represents the principal quantum number, L represents the angular momentum quantum number. N takes values 1, 2, 3, 4 like this. L takes values 0, 1, 2, 3, 4 like this, isn't it? And X is nothing but the number of electrons in that particular orbital. For example, you can see here 1s2. I have written 1s2. What does it mean? It means that the 1s orbital contains 2 electrons. Okay, so we use this type of notation while writing the electronic configurations of the elements. Okay, an orbital diagram or orbital box diagram is a way of representing the electronic configuration of an atom, isn't it? Here arrows or half arrows are used to represent the electrons occupying the orbitals. Arrows or half arrows can point up or down, isn't it? Electrons with up spin or electrons having clockwise spin are drawn either as upward pointing arrows like this or half arrows like this. Next, electrons with down spin, that is counterclockwise spin or anti-clockwise spin, are drawn either as downward pointing arrow like this or half arrows like this. So we use these arrows to represent electrons occupying the orbitals, isn't it? Now I am going to show you how orbital box diagrams are used to represent electronic configurations. See here. Here I am taking an example of helium atom He. Its atomic number is 2. The number of protons is 2. The number of electrons is also 2. And this is the nucleus of helium atom. And around this nucleus, 2 electrons revolve in the first orbit like this. So these are the 2 electrons revolving around the nucleus of helium atom. And you can observe, you can see here, these electrons have self-rotation to they are rotating about themselves while rotating around the nucleus, and this self-rotation is called as the spin. And I will use upward pointing arrows or downward pointing arrows to represent these electrons in an orbitals, and orbitals are drawn by boxes or ovals, isn't it? First I will place these two electrons in 1s orbital. You can see here. See here, these two electrons have opposite spin. This electron has clockwise spin and this electron has anti-clockwise spin. So I will use upward pointing arrow to represent the electron having clockwise spin, and I will use downward pointing arrow to represent the electron having anti-clockwise spin. First I will place these two electrons in a box, and that box is used to represent orbital. So this is the 1s orbital. First I will put these two electrons into this box. See here, this electron is spinning like this, a clockwise spin. It has anti-clockwise spin. So from now onwards I will not use these electrons everywhere. Instead I will use arrows, upward arrows and downward arrows to represent the electrons. So this upward pointing arrow represents the electron having the clockwise spin, and the downward pointing arrow represents the electron having the anti-clockwise spin. Okay, so we can use these arrows, or even half arrows are also used to represent the electrons in an orbital like this. So this half arrow, upward half arrow, represents this electron, and this downward pointing half arrow represent this electron, isn't it? Now let us study the important rules for filling orbitals. We must follow 3 rules while filling orbitals. What are those 3 rules? Let us study one by one by taking an example. The 3 rules that must be followed while writing the electronic configuration of elements are: the first rule is the half-bow principle. It states that electrons occupy orbitals in the increasing order of orbital energy level. That is, the lower energy orbitals are occupied at first, then higher energy orbitals. The energy of any orbital is calculated by its n plus L value, isn't it? So how the energy of the orbitals are calculated, we can see later. The second rule is Hund's rule of maximum multiplicity. All the subshells in an orbital must be singly occupied before any subshell is doubly occupied. For example, if any subshell has more than one orbital, these orbitals are singly occupied before they are W occupied. That is, all the orbitals should be filled by single electrons. Then pairing will be taken place. That I will show you later. Next, Pauli's exclusion principle, it states that no two electrons can have equal values for all four quantum numbers. Consequently, each subshell of an orbital can accommodate a maximum of two electrons, and both these electrons must have opposite spins. That means in any atom, no two electrons do not have the four quantum numbers equal. They at least differ in spin quantum number. So it restricts that any orbital has a maximum of two electrons only. That means we can accommodate a maximum of two electrons in any single orbital. Okay. Now let us study the rules in detail. Now I am explaining the first rule, half-bow principle. The word half-bow is German for building up. The half-bow principle, also called the building up principle, and it states that electrons occupy orbitals in the order of their increasing energy. That is, lower energy or orbitals are filled at first, then higher energy orbitals are filled. So the n plus L value of any orbital gives its energy level. If two orbitals have the same n plus L values, then the orbital which has the lower n value will have the lower energy. You can see here n plus L rule I am showing you. By using n plus L values of any orbital, we can know the energy of that particular orbital. See here, in neutral isolated atom, the lower the value of n plus L for an orbital, lower is its energy. However, if the two different types of orbitals have the same value of n plus L, the orbitals with lower value of n has lower energy. This rule is called as the n plus L rule. Here n is the principal quantum number and L is the angular momentum quantum number. N takes values 1, 2, 3, 4 like this. It represents the stationary orbits, that is main orbits or main shells, and L represents the subshells. L takes values 0, 1, 2, 3 like this. So for any orbital, if we calculate its n plus L value, that gives its energy. If two orbitals have the same n plus L value, then the orbital with lower value of n has lower energy, isn't it? See here. Here I am going to show you L value and name of the orbital. Here name of the orbital is there and its L value. Here I am taking 4 orbital S, P, D, F, and their L values are shown right side. You can see here. Name of the orbital is S, its L value is 0. The L value of P orbital is 1. the L value of d orbital is 2 and f orbital is 3. So S, P, D, F, these are the orbitals and their L values are 0, 1, 2, 3 respectively. Okay. Now I am going to calculate N plus L values of some orbitals. Name of the orbital, its N value, its L value and N plus L value. See here, 1s orbital. The N value, this gives N value. The N value of 1s orbital is 1. Just now I have shown you the L value of s orbital is 0. So N plus L value of 1s orbital is 1 plus 0 is 1. Similarly, 2s orbital N value is 2, L value is 0 and N plus L value is 2. So if you compare the N plus L values of both these orbitals, N plus L value is more for 2s orbital than 1s orbital. Therefore, 1s orbital has less energy than 2s orbital. So electrons enter 1s orbital before they entering into 2s orbital like this. Next, 2p. Here the N value of 2p orbital is 2 and the L value of p orbital is 1. Just now you have seen that. And N plus L value 2 plus 1 equal to 3. 2 plus 1 equal to 3. Now you can see here. Energy of 1s orbital is less than 2s orbital. The energy of 2s orbital is less than 2p orbital. So these orbitals are filled in this order only, 1s, 2s, 2p like this. Next, 3s orbital, its N value is 3 and L value is 0. 3 plus 0, N plus L, 3 plus 0 is 3. Now you can see here, the N plus L value of these two orbitals, that is 2p and 3s orbitals, is same. The N plus L values are same for these two orbitals. Okay, but this orbital has N value less. The N value is less for 2p orbital. That's why its energy is lower than 3s orbital. Next, 3p, N value is 3, L value is 1, N plus L value equal to 4. Similarly, 4s orbital, 4 plus 0, 4. You can see again here also 3p and 4s orbitals are there. The N plus L values of these two orbitals are same, but this orbital has lower N value. That's why the energy of 3p orbital is less than the energy of 4s orbital. Next, 3d orbital, and the N value of 3d orbital is 3 and its L value is 2, isn't it? So 3 plus 2 equal to 5. So these are the N plus L values of some orbitals. In this way we have to calculate all the remaining orbitals. Now electrons fill 1s orbital at first, then they enter into 2s, then 2p, then 3s, then 3p, then 4s, then 3d. So in this order only these orbitals are filled. So I will show you one diagram, that is a Molar diagram, to represent, to remember the order of filling the orbitals easily. Increasing order of the energy of the orbitals is like this. 1s is less than 2s, is less than 2p, is less than 3s, like this. I have calculated the N plus L values up to here, and the remaining orbitals n plus L values can also be calculated like this, and this is the order of increasing order of the energy of the orbitals. So we should remember one thing. So in this order only electrons fill these orbitals. So first electrons enter into 1s orbital. Once it is filled, they enter into 2s orbital. Once it is filled, they enter into 2p orbitals like this. Okay, so this is the increasing order of the energy of the orbitals. And there is a diagram which is used to represent the order of the energy of the orbitals, and this diagram has been given by Molar. That's why its name is Molar chart or Molar diagram. Here I am showing it. Molar diagram, or we can say it as chart also. N equal to 1, that is the first orbit. We have 7 orbits in total. So n equal to 1, that is first orbit has only 1s orbital. N equal to 2. The second orbit contains 2 subshells, namely 2s and 2p. When n equal to 3, we have 3 subshells, 3s, 3p, 3d. N equal to 4, we have 4 subshells, 4s, 4p, 4d and 4f. N equal to 5, 5s, 5p, 5d, 5f. In the sixth orbit again we have 4 subshells, 6s, 6p, 6d, 6f. When n equal to 7, that is in the seventh orbit we have 4 subshells, namely 7s, 7p, 7d and 7f. Now, how these orbitals are filled by the electrons, isn't it? So we have to draw a line like this, isn't it? I am going to draw an arrow through 1s. Parallel to that arrow, I will draw one more arrow like this, and the orbitals which are passed by these arrows are filled in that order only. So first 1s orbital is filled. Then let us draw one more arrow parallel to this arrow. See here, this arrow is passing through 2s only. So after filling 1s orbital, 2s orbital is filled. Next, let us draw one more arrow parallel to this arrow, and this arrow is passing through 2p and 3s. So in that order only electrons fill the orbitals. So 1s is filled first, next 2s, 2p, then 3s. Let us draw one more arrow parallel to this, and this arrow is passing through 3p and 4s. Next, it is passing through 3d, 4p, 5s like this. Okay, so the arrows which are passing through the orbitals, isn't it, represent this arrows represent the way of filling the orbitals, isn't it? So first 1s orbital is filled, then 2s orbital is filled, then 2p, next 3s, next 3p, 4s, 3d, 4p, 5s like this, isn't it? So by using this Molar diagram, we can write the increasing order of the energy of the orbitals like this only. 1s less than 2s, that is energy of 1s is less than 2s, the energy of 2s is less than 2p, it is less than 3s like this. So electrons fill the orbitals in this order only. Clear? Now I will show you the half-bow principle by taking an example. Beryllium Be, its atomic number Z equal to 4. The nucleus of beryllium has 4 protons and 4 electrons revolve around the nucleus. 2 electrons in the first orbit and the remaining 2 electrons in the second orbit. Isn't it? So totally 4 electrons are there to fill the orbitals. Now this is the increasing order of the energy of the orbitals. You can see here. So first I will draw 1s orbital, isn't it? So the first electron enters into 1s orbital. The second electron pairs up with this electron in 1s orbital. So after filling the 1s orbital, electrons should enter into 2s, but here I am entering into 2p orbital. Isn't it? You see here. So the third electron enters into one of the empty orbitals of 2p here. I am placing the fourth electron here. Now observe this electronic configuration, that is the distribution of electrons into various orbitals. It is wrong. Why? Because once 1s orbital is filled, the electrons should enter into 2s orbital, but they are entering into 2p orbital. So it is violating Hubble principle. Now I will show you the correct way of filling the orbitals. Let us take these electrons back into the orbitals. First electron, second electron is there, third electron, isn't it? Next fourth electron. So 4 electrons are revolving around the nucleus. Now 1s orbital is there. First I am drawing 1s orbital. The first electron in the first orbit fills 1s orbital. The second electron pairs up with this electron. Now we have to draw 2s orbital. You see here 1s and 2s. So the third electron enters into 2s orbital. The fourth electron pairs up with this electron. Okay, so this is the correct electronic configuration, isn't it? Previously it was violating Hubble principle. Now it is correct. So the electronic configuration of beryllium is 1s2 2s2, that is in 1s there are 2 electrons and in 2s there are 2 electrons. Okay. Now let us study the Hund's rule in clear. What is Hund's rule? Every orbital in a subshell is singly occupied with 1 electron before any one orbital is doubly occupied, and all electrons in singly occupied orbitals have the same spin, isn't it? For example, if any subshell has more than one orbital, that is equi-energy orbitals, then all the equi-energy orbitals should be filled by one electron at first, then pairing will be taken place. According to this rule, electron pairing in p, d and f orbitals cannot occur until each orbitals of a given subshell is singly occupied. We know we have 3 p orbitals and 5 d orbitals and 7 f orbitals, and all these orbitals are singly occupied at first, then they are doubly occupied, isn't it? See here, example, carbon is there. Here I am showing you the Hund's rule by taking an example, carbon. The atomic number Z equal to 6. That means the nucleus of carbon has 6 protons and 6 electrons revolve around the nucleus. First 2 electrons in the first orbit and the remaining 4 electrons revolve in the second orbit. Now we have to fill these electrons into various orbitals. First here I am drawing 1s orbital. So the first electron enters into 1s orbital. The second electron will also enter into 1s orbital. Next, I will take 2s. After filling 1s orbitals, we know electrons enter into 2s orbital. So the third electron, say this electron enters into 2s, and say the fourth electron pairs up with this electron in 2s orbital. So 2s orbital is completely filled, then electrons enters into 2p orbital. So we have 3 degenerate 2p orbitals, say 2px, 2py, 2pz. All these 3 orbitals have the same energy. That's why they are called as the degenerate orbitals. So in 2p we have more than one orbital. At that time, all these 3 orbitals should be occupied singly at first, isn't it? Then pairing will be taken place. You see here. Next, the fifth electron enters into this orbital, one of the empty orbitals of the 2p. Next, the last electron is also entering into the same orbital and pairing up with the previous one. Now it is violating Hund's rule. Why? Because here each orbital should be singly occupied at first, then they should be doubly occupied. So what is wrong here? Here 2 electrons are put in the same orbital even though empty orbitals are available. So it is violating Hund's rule, isn't it? Now let us take the electrons back into their orbits. Again I will fill the orbitals in the correct way, isn't it? Next, second electron is going there, third electron, isn't it? Next, fourth electron, next, fifth electron, next, sixth electron. So totally 6 electrons are revolving around the nucleus. Now I have to distribute these electrons into various orbitals according to the given rules. So 1s orbital, first electron enters into 1s orbital, second electron pairs up with the previous electron in 1s orbital. Now electrons enter into 2s orbital. So third electron, say this one, enters into 2s, and the fourth electron, say this one, pairs up with this electron. Okay. Next we have to draw the 2p orbital. Okay. Now the fifth electron, say this one, enters into one of the empty orbitals of 2p, and the sixth electron will enter the remaining empty orbitals. It does not pair up with this electron. So this is the correct way of distributing the electrons into orbitals. Okay, so now it is following Hund's rule. So the electronic configuration of carbon is 1s2, 2s2, 2p2. Okay. Next, rule 3, that is Pauli's exclusion principle. I have already defined this principle. According to this principle, no two electrons in an atom will have the same value of all the four quantum numbers. If one electron in an atom has the quantum numbers, say n equal to 1, L equal to 0, M equal to 0 and S equal to plus 1 by 2, no other electron can have the same four quantum numbers. In other words, we cannot place two electrons with the same value of spin, that S means spin, in a 1s orbital. See here, that means in any atom, no two electrons will have the same four quantum numbers equal. They at least differ in their spin quantum numbers, because we have only two numbers. Spin quantum number will take only two values, plus 1 by 2 and minus 1 by 2. For clockwise spin, we are taking plus 1 by 2. For anti-clockwise spin, we are taking minus 1 by 2. Okay, so here is an example for Pauli's exclusion principle. You can see here, isn't it? So here I am taking lithium atom, atomic number Z equal to 3. Its nucleus has 3 protons and 3 electrons revolve around the nucleus. The first 2 electrons are there in the first orbit and the third electron is there in the second orbit. Okay, now we have to fill these 3 electrons into the orbitals. 1s orbital. So the first electron enters into 1s orbital, and let us write the 4 quantum numbers for this electron. See here, n equal to 1, L equal to 0, M equal to 0 and S equal to plus 1 by 2. N is the principal quantum number, L is the angular momentum quantum number and M is the magnetic momentum quantum number and S is the spin quantum number. And for this electron, these are the 4 quantum numbers. Isn't it? Now, it is nothing but the address of this electron. You can say by giving these 4 numbers means it gives the address of this electron. Now, let us take the second electron. This is the second electron I placed in the same 1s orbital. Now, the 4 quantum numbers for this electron are n equal to 1. See here, this is n value and it is there in s orbital, means the L value of s orbital is 0 and m values are from minus L to plus L, that is minus 0 to plus 0 means m value is also 0, isn't it? So here this spin, this half arrow is pointing downwards. It means that the spin value of that electron is minus 1 by 2. Isn't it? So here these two electrons have the same values of N, L, M, but they differ in their S values. Isn't it? That means we can put a maximum of 2 electrons only. If you try to place this electron in the same orbital, see what happens. If you want to write the 4 quantum numbers for this, again we have to write these quantum numbers only. That means it violates the Pauli's exclusion principle. It says that no two electrons in any atom will have the 4 quantum numbers equal. So we should not place this electron in this orbital because this orbital can accommodate a maximum of 2 electrons only, but I placed 3 electrons. That means it is violating Pauli's exclusion principle. Okay, so let us take these electrons back into their positions, isn't it? And fill them in the correct way. Okay, see here. 1s orbital is there. The first electron enters into 1s orbital, isn't it? It is pointing upwards. Second electron pointing downwards. So 1s orbital is completely filled. Then we have to draw the 2s orbital. The third electron enters into 2s orbital. This is the correct way of writing the electronic configuration of lithium. So this one is the right one. It is not violating Pauli's exclusion principle. So the electronic configuration of lithium is 1s2 2s1. Okay, so these are the 3 rules that must be followed while writing the electronic configuration of any element. Okay, before start writing the electronic configuration, so the first 20 elements I am going to arrange some orbitals in their increasing order of energy. See here, I am going to arrange the orbitals in this way, increasing order of energy. So you can see all the orbitals are here. 1s orbital has the least energy than any other orbital. So I will place 1s orbital here. Next, 2s orbital, that is 2s orbital has more energy than 1s orbital. That's why I have placed it above 1s. Next, 2p orbital. Next, 3s orbital. Above that, we have 3p orbital. Next, 4s orbital. Above that, we have 3d orbital. Next, 4p. Next, 5s. Next, 4d. 5p. 6s. Like that, we can arrange all these orbitals in this manner only. Okay, so I'm not going to arrange all these orbitals in this manner because I'm going to write the electronic configurations of the first 20 elements only, and this much arrangement is enough for them. So electrons fill the orbitals in this way. 1s is filled first, next they enter into 2s. Once it is filled, they enter into 2p. Once it is filled, they enter into 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, like this. Isn't it? So let us start writing the electronic configurations of the elements now. Now let us start writing the electronic configuration of the first 20 elements in the periodic table. So the first element in the periodic table is hydrogen, H. Atomic number is 1. Number of protons present in the hydrogen atom is 1, and the number of electrons is also 1. So the nucleus of hydrogen has 1 proton and 1 electron is revolving around this nucleus, and we have to fill this electron into these orbitals. So I have arranged all these orbitals in their increasing energy order. So electrons fill 1s orbitals first, next 2s orbital, next 2p, like this. So we have only one electron. That electron occupies 1s orbital. Okay, so what is the electronic configuration now? Hydrogen has only one electron that is there in 1s orbital. So electronic configuration of hydrogen is 1s1. Next element is helium He. Atomic number 2, number of protons 2, number of electrons 2. The nucleus has 2 protons and 2 electrons revolve around this nucleus in the first orbit, and we have to place these electrons in the orbitals. The first electron enters into 1s orbital. The second electron pairs up with this electron. So the electronic configuration of helium is 1s2. Okay. Next, the third element is lithium, Li. Its symbol is Li. Atomic number is 3. Number of protons 3. Number of electrons is 3. So the nucleus of lithium has 3 protons and 3 electrons revolve around this nucleus. In the first orbit, 2 electrons are revolving, and in the second orbit, n equal to 2, 1 electron is revolving. Now we have to distribute these 3 electrons into these orbitals as per the above 3 rules. So the first electron enters into 1s orbital. Second electron pairs up with this electron. Next, third electron enters into 2s orbital. Why? Because once 1s orbital is completely filled, electrons enter into 2s orbital. Okay, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. In this way, orbitals are filled. Okay, so what is the electronic configuration now? It is 1s2, 2s1. And in short way, we can write the electronic configuration by prefixing helium configuration like this. You see here, helium 2s1. That means before 2s1, helium configuration is there. Helium, neon, argon, krypton, xenon, radon. These are the inert gas elements. So while writing the electronic configurations, we can base these elements, isn't it? Because they have stable electronic configuration that you will learn later in chemical bonding. So helium 2s1, because first orbit is completely filled. So before 2s1, we have helium configuration, that is 1s2. Okay. Now let us write the electronic configuration of beryllium Be. Its atomic number is 4, number of protons 4, number of electrons 4. The nucleus of beryllium has 4 protons and 4 electrons are revolving around the nucleus. 2 electrons in the first orbit and the remaining 2 electrons in the second orbit. That means first orbit can accommodate a maximum of 2 electrons, whereas second orbit can accommodate a maximum of 8 electrons. So we have to fill these 4 electrons into the various orbitals. The first electron enters into 1s orbital. Second electron pairs up with this electron. Next, 1s is filled, electrons enter into 2s orbital, isn't it? And the last electron, that is fourth electron, filled into 2s orbital. So in this way, the electronic configuration. In 1s we have 2 electrons and in 2s there are 2 electrons. So the electronic configuration of beryllium is 1s to 2s2. Otherwise, in short way we can write it as helium 2s2. That is, before 2s2 we have helium configuration, isn't it? Next, the next element in the periodic table is boron B. Its atomic number is 5. Number of protons present in the nucleus of boron is 5. Number of electrons is also 5. So 5 protons are there in the nucleus and 5 electrons revolve around the nucleus. Isn't it? So totally we have 5 electrons to arrange in the orbitals. So the first electron, this one, enters into 1s orbital. Second electron pairs up with this electron. So 1s orbital is completely filled. Then electrons enter into 2s orbital, isn't it? Next, fourth electron pairs up with this electron, and once 2s is filled, electrons enter into 2p orbital, isn't it? So the electronic configuration of boron is 1s2, 2s2, 2p1, or helium 2s2, 2p1. Before this outermost configuration we have helium configuration. Okay, so 2s2 2p1 is the outermost electronic configuration of boron. Before that we have helium configuration. Okay, so this is the electronic configuration of boron atom. The next element is carbon C, atomic number 6, number of protons 6, number of electrons 6. 6 protons are there, 6 electrons revolve around the nucleus, 2 in the first orbit and the remaining 4 in the second orbit. So we have to distribute these 6 electrons into these orbitals as per the rules. Okay, so the first electron enters into 1s orbital. Second electron pairs up with this electron, isn't it? So 1s orbital is completely filled. Then electrons enter into 2s. Next electron enter into 2s orbital, and the fifth electron enters into one of the empty orbitals of 2p, isn't it? And the last electron is also called as a discriminating electron, occupies the another empty orbitals of 2p, isn't it? So this electron will not pair up with this electron. If it pairs up with this electron, means it is violating Hund's rule. So according to Hund's rule, all these 3 orbitals are singly filled at first, then they are doubly filled. So the electronic configuration of carbon atom is 1s2, 2s2, 2p2, or helium 2s2, 2p2. Okay. The next atom or element is nitrogen in the periodic table. Its atomic number is 7. 7 protons are there in its nucleus and 7 electrons revolve around the nucleus. So this is the nucleus of nitrogen, isn't it? It has 7 protons. Neutrons are also there in the nucleus, but for our convenience I am not showing the number of neutrons present in the nuclei. Okay, so 7 protons are there and 7 electrons revolve around the nucleus. Okay, so totally 7 electrons are there to fill. So we have to fill from the inner electrons. Okay, so first electron enter into 1s orbital. Second electron pairs up with this electron in 1s. Next, 1s orbital is completely filled. Electrons enter into 2s orbital, isn't it? Then the fourth electron pairs up with this electron, isn't it? Next, electron enter into 2p. Next electron enters into the empty orbitals of 2p, and the last electron, that is the discriminating electron, enters into the remaining empty 2p orbitals. Okay, so here the electronic configuration, that is, you can see here all the three p orbitals are singly occupied at first according to Hund's rule. Then they are doubly occupied. If any electron comes at next, that electron will pair up with this electron, that is pairing will be taken place from the next electron onwards in 2p. So the electronic configuration is 1s2, 2s2, 2p3. Otherwise, we can write this electronic configuration as helium 2s2, 2p3. Before this outermost configuration, we have the inert gas element helium configuration. Okay. Now let us move to the next element, oxygen. Its symbol is O, atomic number is 8, number of protons 8, number of electrons 8. So the nucleus of oxygen has 8 protons, 8 electrons are revolving around this nucleus, 2 in the first orbit and the remaining 6 in the second orbit. So totally we have 8 electrons to distribute into the various orbitals. Okay, so 1s is filled completely, next 2s is filled, next 2p is filled, like this. Okay, so the first electron in the first orbit enters into 1s orbital. The second electron pairs up with this electron. So 1s orbital is completely filled. Then electrons enters into 2s. Third electron enters into 2s, isn't it? Fourth electron pairs up with this electron. So next electrons enter into 2p orbitals, isn't it? So the fifth electron enters into one of the empty orbitals of 2p. Next electron occupies the remaining empty orbital, and the next electron enters into the third empty orbital. So these three orbitals are singly filled. So the last electron pairs up with the electron in the first orbital here. Okay, so pairing has been taken place. Okay, so the electronic configuration of oxygen atom is 1s2, 2s2. In 2p we have 4 electrons. Otherwise you can write it as helium 2s2, 2p4. That is, before 2s2, 2p4 we have helium configuration. Okay. Next, fluorine, F. The atomic number of fluorine is 9. Number of protons is 9. Number of electrons is 9. This is the nucleus of fluorine atom. 9 protons are there and 9 electrons are revolving round this nucleus. So we have to distribute these 9 electrons into various orbitals. So the first electron enters into 1s orbital. Second electron also enters into 1s orbital. Next, third electron enters into 2s, and fourth electron pairs up with this electron. Next, fifth electron enters into 2p, isn't it? Sixth electron enters into this empty orbital. Next, seventh electron enters into the remaining empty orbital. Next, eighth electron enters into this, that is pairs up with this electron, and the last electron, that is a discriminating electron, final electron, that is the ninth electron, enters into this orbital. Okay, so this is the electronic configuration of fluorine. So 1s2, 2s2, 2p5. In 1s there are 2 electrons, in 2s there are 2 electrons, in 2p there are 5 electrons, isn't it? So here electrons are shown half arrows pointing upward, pointing downward. Pointing upward arrow means electron having clockwise spin. Pointing downward arrow means it represents the electron having counterclockwise spin, that is anti-clockwise spin. So this electronic configuration can be written in the short way as helium 2s2 2p5. Okay. The next element in the periodic table is neon. Its atomic number is 10. It has 10 protons in its nucleus and 10 electrons revolve around the nucleus. So 10 protons are there in the nucleus of neon. 10 electrons are revolving around this nucleus, 2 in the first orbit, and the remaining 8 electrons revolve around the nucleus in the second orbit. So on whole we have 10 electrons to distribute into various orbitals. Okay, so these orbitals have been arranged as per their increasing energy. Okay, so the first electron enters into 1s orbital. Second electron, this one, pairs up with this electron. Next, third electron enters into 2s, and the fourth electron pairs up with this electron, isn't it? So 2s orbital is completely filled. Then electrons enter into 2p orbitals. So the fifth electron enters into 2p, isn't it? Next, sixth electron enters into another empty orbital of 2p, isn't it? So next, the seventh electron enters into this empty orbital. Next, eighth electron pairs up with this electron here, isn't it? Next, ninth electron pairs up with this electron. Finally, the last electron pairs up with this electron. Okay, so totally we have 10 electrons distributed into the various orbitals. So the electronic configuration of neon is 1s2, 2s2, 2p6. Or we can write it as helium 2s2, 2p6. Okay, so neon is also an inert gas element and it is the stable element, isn't it? It has least reactivity and it has a stable configuration. The electronic configuration of neon is very stable. For that reason, for the next coming elements, while writing the electronic configuration, I will base neon in writing the electronic configuration. Okay. Next element is sodium, that is natrium. Natrium means Latin name. So the nucleus of sodium has 11 protons. Atomic number is 11, number of protons is 11, number of electrons is also 11. 11 protons are there and 11 electrons are revolving around this nucleus in different orbits. N equal to 1, N equal to 2, N equal to 3. Isn't it? So first orbit we can put a maximum of 2 electrons only, and second orbit can accommodate a maximum of 8 electrons only, and third orbit can accommodate a maximum of 18 electrons. We can put 18 electrons on third orbit, isn't it? So first orbit is completely filled, then second orbit is completely filled. So the 11th electron enters into third orbit. This is the 11th electron, last electron. So we have to fill all these electrons from the inner electrons. So the first electron, this one, enters into 1s orbital. The second electron, this one, also enters into 1s orbital. 1s orbital is completely filled. Then the third electron enters into 2s orbital, isn't it? Fourth electron pairs up with this electron, isn't it? Next, the fifth electron, see here, occupies one of the empty orbitals of 2p. Next, sixth electron will occupy the other empty orbital. So 6 electrons have been filled. Next, seventh electron occupies the remaining empty orbital. So all these orbitals are singly occupied by the electrons. Next electron will pair up from here onwards, from this orbit onwards. So 8th electron pairs up with this electron. Next, 9th electron pairs up with this electron, and 10th electron pairs up with this electron. So totally we filled 10 electrons. So the last electron is there in n equal to 3. So second orbit is completely filled, that is 1s, 2s, 2p orbitals are completely filled. Next electrons enter into 3s. So the electron which is revolving in the third orbit enters into 3s orbital. Okay, so the electronic configuration is 1s2, 2s2. In 2p there are 6 electrons, 2p6 and 3s1. So we can write this electronic configuration in short form as 1s2, 2s2, 2p6. This electronic configuration has neon. Neon has this electronic configuration. So instead of writing this much of length, we can write this electronic configuration replacing this electronic configuration by neon electronic configuration before this. So neon 3s1, that means before 3s1 we have neon configuration. Okay. The next element is magnesium. Its symbol is Mg and atomic number is 12. Number of protons 12 and number of electrons 12. So the nucleus of magnesium contains 12 protons and 12 electrons revolve around the nucleus in different orbits. 2 electrons are there in the first orbit and 8 electrons are there in the second orbit and 2 electrons are there in the third orbit. So totally 12 electrons are revolving around the nucleus of magnesium. Now we have to place all these 12 electrons in the various orbitals. Okay, so the first electron enters into 1s orbital. Next, second electron enters into the same orbital. Next, third electron enters into 2s orbital. The fourth electron, this one, enters into the same orbital, isn't it? Next, fifth electron, that is 2s is completely filled. The fifth electron enters into one of the empty orbitals of 2p. Sixth electron enters into another empty orbital, isn't it? Next, seventh electron, say this one, enters into the remaining empty orbital. Eighth electron, say this one, pairs up with the first electron. Next, ninth electron pairs up with this electron. And 10th electron, this one, pairs up with this electron. So 2p orbital is completely filled, isn't it? Next, 2 electrons are there to fill, and once 2p orbital is completely filled, electrons enter into 3s. 11th electron enter into 3s and 12th electron pairs up with this electron in 3s. So we have 1s2, 2s2, 2p6 and 3s2 electronic configuration. So magnesium configuration, electronic configuration is this. In 1s, 2 electrons are there. In 2s, 2 electrons are there. In 2p, 6 electrons are there. In 3s, 2 electrons are there. Or we can write it in short way as neon 3s2. Okay. The next element in the periodic table is aluminium, Al. Its atomic number is 13. It has 13 protons in its nucleus and 13 electrons revolve around the nucleus. This is the nucleus of aluminium, contains 13 protons and 13 electrons revolve around the nucleus, and 2 electrons are there in the first orbit, and we can put a maximum of 8 electrons in the second orbit. 8 electrons are revolving in the second orbit, and we can put a maximum of 18 electrons in the third orbit. But here we have only 3 electrons to revolve in the third orbit, n equal to 3. Now we have to fill all these 13 electrons into various orbitals. So the first electron enters into 1s orbital. The second electron pairs up with this electron, isn't it? And 1s orbital is completely filled. Then third electron enters into 2s, isn't it? Next, fourth electron pairs up with this electron in 2s. Next, fifth electron occupies one of the empty orbitals of 2p. Next, sixth electron occupies the other empty orbitals of the 2p. Next, totally 6 electrons have been filled. Next, seventh electron occupies the remaining empty orbital. So all the 2p orbitals are singly occupied, then pairing will be taken place from the next electron onwards. So 8th electron pairs up with this electron, isn't it? Next, ninth electron pairs up with this electron and 10th electron pairs up with this electron. So totally 10 electrons have been filled. Next, once 2p orbital is completely filled, electrons enter into 3s orbital. So the 11th electron enters into this orbital, that is in 3s orbital. Next, 12th electron, say this one, pairs up with this electron in 3s, and the last electron, that is the discriminating electron, this electron enters into 3p orbital, one of the empty orbitals of 3p. So totally 13 electrons have been filled. So the electronic configuration is 1s2, 2s2. In 2p there are 6 electrons, and in 3s there are 2 electrons, and in 3p there is 1 electron. So 1s2, 2s2, 2p6, 3s2, 3p1, or we can write this electronic configuration in the short way as neon 3s2 3p1. It means that before 3s2 3p1 we have neon configuration. Okay. Next, the 14th element in the periodic table is silicon Si. Its atomic number is 14. It has 14 protons in its nucleus and 14 electrons are there. Okay. Now here I am drawing the atomic structure of silicon here. 14 protons are there and 14 electrons revolve around the nucleus, 2 in the first orbit and 8 electrons are there in the second orbit revolving, and 4 electrons are there in the third orbit. So totally 14 electrons are there to distribute into various orbitals. So first electron, this one, enters into 1s orbital. Second electron pairs up with this electron. Next, 1s orbital is completely filled. Next, we have to fill the 2s orbital. Third electron enters into 2s. Next, fourth electron, say this one, pairs up with this electron. 2s orbital is completely filled. Then electrons enter into 2p. Fifth electron enters into this orbital. Next, sixth electron occupies another empty orbital of 2p. Next, seventh electron occupies the third empty orbital of 2p. Next pairing will be taken place from the next electron onwards, isn't it? So totally how many electrons we have filled so far? 7 electrons. Next, eighth electron pairs up with this electron, isn't it? Next, ninth electron pairs up with this electron, and the 10th electron pairs up with this electron here. So totally 10 electrons have been filled. Next, once 2p orbital is completely filled, electrons enter into 3s orbital. So the 11th electron enters into 3s orbital. Okay. Next, 12th electron, that is say this electron, pairs up with this electron in 3s. So 3s orbital is completely filled. Next electrons enter into 3p. So totally 12 electrons have been filled. 13th electron occupies one of the empty orbitals of 3p, and the last electron, that is the discriminating electron, occupies the other empty 3p orbital. So in this way, the electronic configuration of silicon is 1s2, 2s2, 2p6, 3s2, 3p2. 1s2, 2s2, 2p6, 3s2, 3p2, or we can write it as neon 3s2, 3p2. This is the electronic configuration of silicon, isn't it? Remember, if p orbitals if all p orbitals are singly occupied according to Hund's rule, and all the electrons must have the same spin. That's why in all the electrons, for all these electrons which are singly occupied, I have shown half arrow pointing upward, isn't it? Next element is phosphorus P. Its symbol is P. Atomic number is 15. Number of protons present in the nucleus of phosphorus is 15, and 15 electrons revolve around this nucleus. Here is the atomic structure of phosphorus. I am drawing. First orbit contains 2 electrons. Second orbit contains 8 electrons, and the third orbit contains 5 electrons. Totally 15 electrons are there to fill. So first electron occupies 1s orbital. The second electron pairs up with this electron in 1s. Next, 1s is completely filled. Electrons, third electron enters into this orbital, 2s orbital. Next, say fourth electron pairs up with this electron, 2s orbital is completely filled. Then electrons enter into 2p, isn't it? So fifth electron, say this one, occupies empty orbitals of the 2p. Next, sixth electron, say this one, occupies the remaining empty orbital. Next, seventh electron occupies this orbital. Okay, so 2p orbital is completely, that is singly filled completely. Then pairing will be taken place. So 8th electron, say this one, pairs up with this electron. These two have opposite spin. Next, 9th electron will pair up with this electron, and finally this electron. Okay, so 10 electrons have been filled. Next, still we have 5 electrons to fill into the various orbitals, and once 2p orbital is completely filled, electrons enter into 3s orbital. So 11th electron enter into 3s, and 12th electron, say this electron pairs up the electron in 3s. Next, 12 electrons are over, isn't it? So 3s orbital is completely filled. Next electron, that is 13th electron, enters into one of the empty orbitals of 3p, and 14th electron occupies the other empty orbital of 3p, and the 15th electron occupies the other empty orbital of 3p. That is, all these 3p empty orbitals have been singly filled, and I have shown all the half arrows pointing upwards. It means that all these singly occupied orbitals, that is these electrons, have the same spin. Okay, so then what is the electronic configuration now? 1s2, 2s2, 2p6, 3s2, 3p3. This is the electronic configuration of phosphorus, or we can write this in the short way as neon 3s2, 3p3. Okay, so before 3s2, 3p3 we have neon configuration. The 16th element in the periodic table is sulfur. Yes, its atomic number is 16. Number of protons 16. Number of electrons 16. 16 protons are there in the nucleus of sulfur. 16 electrons revolve around the nucleus in different orbits. In the first orbit there are 2 electrons, and in the second orbit there are 8 electrons, and third orbit has 6 electrons. Totally 16 electrons are there to fill in the orbitals. Okay, so the first electron enters into 1s orbital. The second electron pairs up with this electron. Next, third electron enters into 2s. Fourth electron occupies the same orbital. Next, 2s orbital is completely filled. Then fifth electron enters into 2p. Next, sixth electron enters into another 2p empty orbital. Next, seventh electron enters into the other empty 2p orbital. Eighth electron pairs up with this electron. Ninth electron will pair up with this electron, and 10th electron will pair up with this electron. So totally 10 electrons have been filled. Still 6 electrons are there in the third orbit. We have to fill them. So once 2p orbital is completely filled, electrons enter into 3s. So 11th electron enter into 3s orbital, isn't it? And the 12th electron, say this electron pairs up with this electron. Next, 12 electrons have been filled. 13th electron enters into one of the empty orbitals of 3p, and 14th electron enters into another empty orbital of 3p. Next, 15th electron enters into the third empty orbital of 3p, isn't it? So the last electron enters into the 3p orbital. Okay, so it has paired up with the first electron. So totally 16 electrons have been filled. So the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p4. Okay, or we can write it as neon 3s2, 3p4. Okay. The next element in the periodic table is chlorine, Cl. Its atomic number is 17. Number of protons present in the nucleus is 17, and the number of electrons revolving round the nucleus is 17. So 17 protons are there in the nucleus of chlorine. 17 electrons revolve round this nucleus in the various orbits. So first orbit has 2 electrons, second orbit has 8 electrons, and the third orbit has 7 electrons. Totally 17 electrons are there to fill into the various orbitals. So the first electron enters into 1s orbital. Second electron pairs up with this. Next, third electron enters into 2s orbital. Fourth electron pairs up with this electron. Next, fifth electron occupies 2p, one of the empty orbitals of 2p. Next, sixth electron occupies another empty orbital of 2p. Next, seventh electron occupies the third empty orbital of 2p. Okay, so all the 2p orbitals are singly occupied. Then pairing will be taken place from the next electron onwards. So 8th electron pairs up with this electron, isn't it? Next, 9th electron will pair up with this electron, and 10th electron will pair up with this electron. So totally 10 electrons have been filled. Still 7 electrons are there. So once 2p orbital is completely filled, electrons enter into 3s. So 11th electron enter into 3s orbital, isn't it? And 12th electron, say this one, occupies 3s orbital. It has paired up with the previous electron in 3s. Next, 3s orbital is completely filled. Once 3s orbital is completely filled, electrons enter into 3p. So 13th electron enters into 3p, isn't it? Next, 14th electron enters into this, and 15th electron occupies the another empty orbital of 3p, and 16th electron pairs up with this electron, and the last electron, say 17th electron, this is called as a discriminating electron, pairs up with this electron in 2p. So totally 17 electrons have been filled. So the electronic configuration of chlorine is 1s2, 2s2, 2p6, 3s2, 3p5, or neon 3s2, 3p5. Okay. The next element in the periodic table is argon, Ar. This is also an inert gas element. It has the stable electronic configuration, and the reactivity is very less for noble gas elements. You will learn later all those things. So argon, next element is argon. Its symbol is Ar. Atomic number is 18. 18 protons are there in its nucleus, and 18 electrons revolve around the nucleus. Okay, this is the nucleus of argon. 18 protons are there. 18 electrons revolve around the nucleus, 2 in the first orbit, 8 in the second orbit, and the remaining 8 in the third orbit. So totally we have 18 electrons to fill the orbitals. So I will fill the first electron into 1s orbital. Second electron pairs up with the previous electron in 1s. Next, 1s orbital is completely filled. Next electron enters into 2s orbital. Say this one. Fourth electron pairs up with this electron in 2s, isn't it? So 2s orbital is completely filled. Next, fifth electron, say this one, occupies one of the empty orbitals of 2p. Next, sixth electron, say this one, occupies the other empty orbital of 2p, isn't it? Next, seventh electron, say this one, occupies the third empty orbital of 2p. Next, eighth electron, say this one, pairs up with this electron in 2p, isn't it? Next, ninth electron, say this one pairs up with this electron, and 10th electron, say this one pairs up with this electron. So totally 10 electrons have been filled. Next, 11th electron enters into 3s orbital, isn't it? So 11th electron, say this one enters into 3s orbital. Next, 12th electron, this one, say pairs up with the previous electron in 3s. So totally 12 electrons have been filled. Next, 13th electron occupies one of the empty orbitals of 3p, because 3s orbital is completely filled, then electrons enter into 3p. So 13th electron enters into one of the empty orbitals of 3p. Next, 14th electron occupies the other empty orbital of 3p, isn't it? Next, 15th electron, say this one, occupies the third empty orbital of 3p, isn't it? Next, 16th electron pairs up with this electron, isn't it? Next, 17th electron, say this one pairs up with this electron. According to Hund's rule, pairing will be taken place once all the orbitals are singly occupied. Next, the last electron, that is the discriminating electron, 18th electron, pairs up with this electron in 3p. So totally 18 electrons have been filled in the various orbitals. Okay, so then what is the electronic configuration now? 1s2, 2s2, 2p6, 3s2, 3p6, or neon 3s2, 3p6. Before 3s2, 3p6, we have neon configuration. Okay. The next element in the periodic table is potassium. Its symbol is K. The Latin name of potassium is Kalium. So its symbol was derived from its Latin name Kalium. So atomic number of potassium is 19. Number of protons present in its nucleus is 19, and the number of electrons present is also 19. Okay, so 19 protons are there and 19 electrons revolve around the nucleus in different orbits. In the first orbit, 2 electrons revolve, and in the second orbit, 8 electrons revolve, and the third orbit, 8 electrons are revolving. Actually, third orbit can accommodate a maximum of 18 electrons. But in this case, once 3p orbital is completely filled, electrons will not enter into 3d. Even though 3d orbitals are there in the third orbit, they will not be filled. They are not filled unless 4s is filled, because the n plus L value of 3d orbital is 3 plus 2 is 5, whereas the n plus L value of 4s orbital is 4 plus 0 is 4. So the energy level of 4s orbital is less than 3d orbital. Hence, electrons, that is 19th electron, will enter into 4s orbital rather than 3d orbital. Okay, so actually third orbit can accommodate a maximum of 18 electrons, but here 8 electrons are completely occupied third orbit. So next 19th electron revolve in the fourth orbit, n equal to 4, because 4s orbital is there in the fourth orbit. So totally 19 electrons are there to fill. Okay, so first electron occupies 1s orbital, Second electron also occupies the same orbital. Next, third electron occupies 2s orbital. Next, fourth electron, say this one pairs up with this electron, isn't it? Next, fifth electron, say this one occupies one of the empty orbitals of 2p, and sixth electron, say occupies another empty orbital of 2p. Next, seventh electron occupies the third empty orbital of 3p, isn't it? Next, eighth electron occupies this orbital again, isn't it? Pairing is being taken place. Okay, so ninth electron occupies this and pairs up with this electron, and 10th electron, say, pairs up with this electron. So totally 10 electrons have been filled. Next electron, say 11th electron enters into 3s orbital. Say this electron enters into 3s. Next electron, that is 12th electron, enters, say this electron enters into 3s orbital only. It pairs up with the previous electron in 3s orbital. Next, 13th electron occupies one of the empty orbital of 3p, isn't it? Next, 14th electron, say this one occupies the other empty orbital of 3p, isn't it? Next, 15th electron, say this one occupies the third empty orbital of 3p. Now pairing will be taken place. So 15 electrons have been filled, isn't it? 2, 2, 4, 4 and 6, 10, 10 plus 2, 12 plus 3, 15. So 16th electron pairs up with this electron, isn't it? Now 17th electron, say this electron pairs up with this electron in 3p, and 18th electron, say this one pairs up with this electron. So 3p orbital is completely filled. So 3d orbitals are there in third orbit only. Even though 3d orbitals are there in third orbit, they will not be filled before 4s, isn't it? So once 3p orbital is completely filled, electrons enter into 4s instead of 3d, because the n plus L value of 4s is less than 3d. That is, the energy of 4s is less than 3d. So the 19th electron, say this one occupies 4s orbital. So totally 19 electrons have been filled. So the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Okay, so up to to 3p, Argon electronic configuration is there. 1s2, 2s2, 2p6, 3s2, 3p6. This configuration belongs to Argon. So instead of writing this lengthy configuration, we can shorten this configuration like this: Argon 4s1. That means before 4s1 we have Argon electronic configuration. Okay. And the next element in the periodic table is calcium. In this video, I already told you I am going to tell you the electronic configurations of the first 20 elements in the periodic table. So this one, calcium, is the 20th element. Calcium is 20th element in the periodic table. Its symbol is Ca. Atomic number is 20. It has 20 protons in its nucleus and 20 electrons are there. 20 electrons are revolving around the nucleus. So 20 protons in the nucleus, 20 electrons are revolving around the nucleus in different orbits. First orbit has 2 electrons revolving. Second orbit has 8 electrons revolving. And third orbit also has 8 electrons revolving. Actually, third orbit can accommodate a maximum of 18 electrons. But once 3p orbital is completely filled, electrons enter into force. That's why 19th and 20th electrons revolve in the fourth orbit. Like this. So totally 20 electrons are there to fill into the various orbitals. So the first electron enters into 1s orbital. Next electron, second electron enters into 1s orbital, isn't it? Third electron, say this one, enters into 2s. Next, fourth electron pairs up with the electron in 2s, isn't it? Next, fifth electron, say this one, occupies one of the empty orbitals of 2p, isn't it? Next, sixth electron occupies the other empty orbital of 2p, isn't it? Next, seventh electron occupies the third empty orbital of the 2p. Okay, so 7 electrons have been filled. 2p orbital is completely filled with single electrons, that is, these orbitals are half filled, isn't it? Then pairing will be taken place from the next electron onwards. So 8th electron pairs up with this electron. Next, 9th electron will pair up with this electron in 2p, and 10th electron will pair up with this electron in 2p. So totally 10 electrons have been filled, isn't it? So still 10 electrons are there to go. So 2p is completely filled. Then electrons enter into 3s. 11th electron enter into 3s, isn't it? Next, 12th electron, say this electron pairs up with the electron already there in 3s. 3s is completely filled. Then electrons enter into 3p. Okay, so 13th electron enter into empty orbital of 3p. Next, 14th electron, say enter into another empty orbital of 3p, isn't it? Next, 15th electron, say this one, enters into another empty orbital of 3p. So all the 3p orbitals are singly occupied. Then pairing will be taken place from the next electron onwards. Okay, so 16th electron will pair up with this electron, isn't it? 17th electron, say this one, will pair up with this electron, isn't it? So next, 18th electron, say this one, will pair up with this electron. So totally 18 electrons have been filled. Still 2 electrons are there. So 19th electron enters into 4s instead of 3d, isn't it? The energy of 4s is less than 3d. So 19th electron enters into 4s orbital, and the last electron, that is the discriminating electron, enters into 4s orbital and pairs up with the electron already there in 4s. Okay, so this is the distribution of 20 electrons related to calcium atom. So what is the electronic configuration? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So the electronic configuration is this. Okay, or we can write this electronic configuration in the short form as Argon 4s2. Before 4s2 we have argon electronic configuration. Okay, so these are the electronic configurations of the first 20 elements in the periodic table. Okay, thank you.